Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last class, we learned the minimization of a sum of products expression using a Karnaugh map. During this session, we focus on minimization of product of sums expression, and also we learn how to effectively include a don't care condition in a K-map for simplification. One more application of K-map, that is conversion between sum of products and product of sums expression, will also be discussed here. With not much introduction, let me start with. We know that a standard product of sums expression contains max terms, and each max term can separately be represented in a K-map. When we did minimization on sum of products expression, we selected ones to form groups, but here a minor modification. Corresponding to each max term, we enter a 0 in the K-map and create groups by recognizing patterns of zeros. Also recall that 0 in max term is symbolized with an uncomplemented variable and 1 using a complemented variable. For example, the term a plus b plus c complement will be mapped to the 0 0 1 cell of a 3 variable K map, and we enter a 0 to that cell. Let us just go through the procedure to obtain the minimized function of a standard product of sums expression. Firstly, draw an empty K map for the given number of input variables. Then identify the binary values which corresponds to each max term given in the expression and enter 0 in the respective cells. The empty cells can be filled with ones or we can leave it blank. Then group zeros to form octets, quads, then pairs. Any isolated 0 can form a group by itself. The entire expression is mapped now. The next step is check whether any redundant groups are formed or not. If yes, remove them. Now reduce the terms of each group and finally AND them. This will produce a minimum product of sums expression. We shall move forward to the minimization problem. We start with a 4 variable expression. Given f of a, b, c, d equal to pi of 0, 1, 3, 5, 6, 7, 10, 14 and 15. First, let us expand the terms in the given variables a, b, c and d. The 0 refers to m0, that is a plus b plus c plus d, and its binary form is 0, 0, 0, 0. The next is 1, that is m1. Its binary form is 0, 0, 0, 1. Then the term is a plus b plus c plus d complement. Next is 3, that refers to m3, and the corresponding binary is 0, 0, 1, 1, which is a plus b plus c complement plus d complement. Next 5, m5, 0, 1, 0, 1. That is a plus b complement plus c plus d complement. Then 6, that is m6. So, the binary 0, 1, 1, 0 and the term is a plus b complement plus c complement plus d. The next is 7, we write m7, that is 0, 1, 1, 1. And the corresponding max term is a plus b complement plus c complement plus d complement. Next 10, that is m10, binary equivalent 1, 0, 1, 0 and the max term a complement plus b plus c complement plus d. Next is 14, m14, 1, 1, 1, 0 and a complement plus b complement plus c complement plus d is the max term. And the last term is 15, which can be symbolized as m15 and the binary equivalent is 1, 1, 1, 1 and the max term is a complement plus b complement plus c complement plus d complement. So, the product of sums expression can be written as f equal to a plus b plus c plus d plus a plus b plus c plus d complement plus a plus b plus c complement plus d complement plus a plus b plus c plus d complement plus a plus b complement plus c complement plus d plus a plus b complement plus c complement plus d complement plus a complement plus b plus c complement plus d plus a complement plus b complement plus c complement plus d plus a complement plus b complement plus c complement plus d complement. The next task is to draw a K-map and represent these terms in the map. So, let us draw a 4 variable K-map. 2 variables A and B across the rows and the other 2 variables C and D across the columns. Then write the column and row headings. It is easy if we also write the binary values corresponding to each row and column. Then map the given expression. Enter zeros in each cell that corresponds to each term of the product of sums expression a plus b plus c plus d, a plus b plus c plus d complement, a plus b plus c complement plus d complement, then a plus b complement plus c plus d complement, a plus b complement plus c complement plus d complement, a plus b complement plus c complement plus d, a complement plus b complement plus c complement plus d complement, a complement plus b complement plus c complement plus d, then a complement plus b plus c complement plus d. There are few empty cells, we can write ones there or leave them blank, we just leave it. The next step is to group zeros. When we observe the map, we can see that no octet is formed, but we find 2 quads and also 2 pairs. No wraparound adjacency is seen here. Now, it is our turn to derive the reduced term from each group. Let me number each group as group 1, group 2, group 3 and group 4. In group 1, the input variables appears in the row are A and B, and they are in the same form A and B in both cases. What about C and D? Value of C remains the same, but the value of D takes both complemented and uncomplemented form. So, let us remove D and we get the reduced term as A plus B plus C. Then consider the next group, group 2. This is a quad. So, 2 variables must be eliminated, right. Let us see how. Check the value of A and B over the quad. A remains constant, but B varies. So, B is eliminated. Then check the values of C and D. C varies, but D is in the same form. D complement. Hence, the final term produced by group 2 is A plus D complement. In the same way, from group 3 we get B complement plus C complement, and from group 4 it is a pair, we get A complement plus C complement plus D. Now, and these terms or get the product of these terms, that is A plus B plus C dot A plus D complement dot B complement plus C complement dot A complement plus C complement plus D. This is the final minimized POS expression. Hope you understood how to simplify a standard POS expression using K-map. K-map simplification is effectively possible when the function is given in standard form. Otherwise, it has to be converted to standard form to proceed with K-mapping. You can refer to conversions of non-standard function to a standard function in the former session. This method can be applied to any POS expression with 2, 3 or 5 variables. We move on to the next topic now, conversion of sum of products or product of sums expression to equivalent product of sums or sum of product expression. When a product of sums expression is mapped, it can be converted easily to its equivalent sum of products expression using K-map. Similarly, the reverse conversion is also possible. While implementing a logic circuit, we look for a simpler circuit that uses less number of logic gates. So, the minimum expressions both in the form of SOP and POS will help us to decide on the circuit that can be constructed easily and efficiently. For a POS expression, we consider the cells that contain zeros. What about the other cell contents? We know that they are ones. So, to obtain the equivalent SOP expression, consider the cells containing ones or consider the cells other than 0 entry. To get the equivalent expression, we need to exempt those cells. To illustrate, consider the logical expression Q equal to A plus B plus C dot A plus B plus C complement dot A plus B complement plus C dot A complement plus B plus C complement dot A plus B complement plus C complement. We are going to represent this expression in a K-map. It is a 3 variable K-map. Mark each term A plus B complement, A complement plus B complement and A complement plus B in the respective rows and C complement in the columns. Now, enter 0 in the corresponding cells. The zeros can be grouped to obtain the minimized product of sums expression. From the quad, we obtain the term A, and from the pair, we get the term B plus C complement. And the simplified product of sums expression is A dot B plus C complement. The same map contains a set of empty cells which are nothing but ones. Let us write all ones in those cells. What is represented by a 1? A product term. So, these ones represent all min terms exist in the sum of products expression equivalent to the given product of sums expression. Hence, grouping of these ones will certainly give us the reduced min terms. Let us mark ones and group them. We get ones in the cells corresponding to 110, 111 and 100. Now, let us group them. We get 2 pairs and the reduced min terms are AB and AC complement. Thus, we obtain the simplified sum of product expression of the given function AB plus AC complement. So, the minimum POS function is A dot B plus C complement. To implement this, we require one AND gate and one OR gate. The minimum sum of products expression is AB plus AC complement, which needs 2 AND gates and 1 OR gate to realize the Boolean function. With much more easiness, we could make simplifications and compare the results for better logic circuit designing. Okay. The next we are going to discuss about don't care conditions. Till now, we were discussing on Boolean expressions where each term either results a 1 or 0 in the truth table. That means, all input combinations were used to produce either a 0 or a 1 for the function, or all input states were valid. But there are certain functions for which some of the input combinations neither gives a 1 value nor a 0 value, or we say such combinations are invalid. Those combinations are known as don't care conditions. It is represented as X in a K-map. For example, you know that in 8421 code, the input combinations 1010, 1011, 1100, 1101, 1110 and 1111 are invalid. Similarly, the input combinations 0000, 0001, 0010, 1101, 1110 and 1111 are unspecific in XS3 code. Any logical circuits using these codes functions under the assumption that these input combinations will never occur. So, we do not care what the output is to be. Then, how do you map those functions to a K-map? What do we do with these don't care conditions? we can't write a 1 because a 1 on the map specifically declare that for a particular input combination the output must be 1. Also, we cannot represent with a 0. So, the symbol X is used to represent a don't care condition in the K-map. The value of X can be assumed as either 0 or 1 as per the requirement. While grouping in the K-map simplification, it may help us to cover a larger group. Thus, we may obtain a more minimized Boolean expression. Also, let me tell you, the X need not be used compulsorily if it is not going to contribute for minimization. To illustrate, let us consider the function f of ABCD equal to summation m1, m3, m7, m11 and m15. And the don't care conditions are d of ABCD equal to summation m0, m2 and m5. The minterms of f produces 1s and minterms of d are known never to occur. Let us bring all these terms to a K-map. Mark 1s in the respective positions of minterms exist in f. Then let us mark don't care conditions from the function d in the cells 0, 0, 0, 0, 0, 0, 1, 0 and 0, 1, 0, 1. As you know, the empty cells represent 0 value. Let me just mark the zeros too. Now, we start grouping ones. Normally, we group like this. Here, we have one pair and one quad. So, the minimized expression will have two terms, each with 3 and 2 variables respectively. And reduced terms of group 1 is A complement B complement D and group 2 is CD, and the final minimum expression is A complement B complement D plus CD. Let this be expression 1. But when you consider X that corresponds to 0, 1, 0, 1, the group becomes a quad and again one more variable is reduced. What if we select don't care cases represented in 0, 0, 0, 0 and 0, 0, 1, 0 cells? Yes, we can create one more group with 4 elements, but one group bring one term to the reduced expression. The ones of this group have already grouped and it is not essential to add those cells. Always include X in the group only if it can form a larger group. Never select a group that contains only X, and always recheck the groups and remove the redundant groups if present. Next, write the Boolean expression for each group, and finally OR them to obtain the minimized expression. Here, from group 1 we obtain A complement D, and from second group we get CD. So, the final expression is A complement D plus CD. This is expression 2. Just compare the expression 1 and 2. Expression 1 requires 3 AND gates and 1 OR gate with 4 input variables to realize the given function, whereas expression 2 uses only 2 AND gates and an OR gate with 3 input variables. This is the advantage of using don't care conditions in a K-map. While mapping product of sums expressions, the don't care conditions are considered as zeros if necessary. Let us refer to one of the application. Most of the digital devices use 7 segment displays to present data to the user. Mostly this information will be numerical data in the form of characters, symbols and numbers. How does these characters and symbols are displayed? Actually, it has 7 segments, and for each digit a set of segments are displayed. For example, a particular segment, say segment A, is displayed when the digits are 0, 2, 3, 5, 6, 7, 8 and 9. We know that every digit can be represented by a BCD code. For each digit, there will be a set of segments which are active, and this table describes the same. To display 0, all segments except G must be active or illuminated. To display 1, only 2 segments are enough, segment B and C. To display 2, all segments except C and F. When we observe each digit, we can say the segments to be activated. Or in another way, the segment A is active for the digits 0, 2, 3, 5, 6, 7, 8 and 9. Segment B is active for the digits 0, 1, 2, 3, 4, 7, 8 and 9, and we know that these numbers can be represented using BCD. So, we can derive a sum of products expression for each segment using the input variables A, B, C and D. This expression can be minimized using a K-map and logically realized. Consider the segment A. As I mentioned, it should be active for the numbers 0, 2, 3, 5, 6, 7, 8 and 9. Then the SOP expression will be A equal to A complement B complement C complement D complement plus A complement B complement C D complement plus A complement B complement C D plus A complement B C complement D plus A complement B C D complement plus A complement B C D plus A B complement C complement D plus A B complement C complement D. Each individual term of this expression represent one of the digit that uses segment A. Let us enter this expression to a K-map. You may remember certain input states that never occur in BCD code. They are 1010, 1011, 1100, 1101, 1110 and 1111. So, they can be considered as don't cares, and we mark X in the respective cells. Now, form the groups and get the reduced expression. We will get the 2 octets, one from last 2 rows and another one from last 2 columns, and they produce the terms A and C respectively. Then 2 more quads, one formed from corner elements that follows wraparound adjacency, and another group formed from middle rows and columns. They bring 2 terms to the minimum expression B complement D complement and B D respectively. Here we see the great advantage of considering don't cares, and finally we get A plus C plus BD plus B complement D complement. This is the reduced expression to design the logic circuit for the segment A. In the same manner, we can obtain the logic expression for all the segments of a 7-segment display. Let us summarize the topics we discussed today. The simplification method of product of sums expression was introduced in this session. The criteria was the minimization of number of literals and number of terms. The only restriction on this method is that the expression must be in standard form. Here we have selected only the max terms and marked 0 corresponding to each term. One of the very significant and useful concept in minimizing the Boolean expression using K-map is the concept of don't cares. These are the input states that neither give a 0 nor 1 to the function, or they do not have any significant effect on the output function. So, they were used conveniently as zeros or ones while grouping, and hence obtained a more simplified expression. As an illustration to the advantage of don't care conditions, the simplified logic for a 7-segment display was also discussed. Here I conclude the session. Hope you enjoyed learning through problems. Thank you for watching. See you in the next session. Bye.